And let's proceed on schedule at 9 o'clock to our next presenter. It is Enzo Yi from the Blythe Academy in University Sherbrooke, Canada. And he's going to talk about Deep Image Translator version 2, analysis of multimodal medical images using semantic segmentation maps generated through deep learning. Go ahead.
Thank you very much. Can you guys hear me?
Yes, very well.
Yes. Thank you, United Scientific Group. Thank you, everyone, for joining this conference. It's an honor to present my work to all of you. So, if I may, can I share my screen?
Yes, please. And we can see your screen.
Thank you so much. So, my work is about the analysis of multimodal medical images using semantic segmentation maps generated through deep learning. And so, like many of you who are in the medical field, you all know that the analysis of multimodal medical images, they require the selection of one or more anatomical regions of interests for the extraction of useful statistics. And the use of spherical and ellipsoid ROIs, regions of interests, may be sufficient for large organs such as the liver and large muscle groups. But for organs and tissues with complex shapes, such as intestines and adipose tissues, the manual selection of ROIs is not a scalable approach. One possible method is to use deep learning for automated segmentation. But many deep learning pipelines for semantic image segmentation generate color-coded segmentation maps stored as image files, while most free software programs for medical image analysis, such as AMIDE, Osiris Lite, 3D Slicer, cannot use these files to generate ROI statistics for multimodal images stored as DICOM files, the most common medical file format. And so we have previously developed a user-friendly software tool for image-to-image translation using deep learning called the Deep Image Translator. And so we are presenting an update to the Deep Image Translator software with an addition of a tool for multimodal image segmentation analysis, the MMM-ISA. We use this program to measure the FDG uptake by the lungs and subcutaneous adipose tissue using whole body scans from ACR-IN. And we compare the measurements performed using the MMM-ISA and those obtained through manual selection of ROIs. And so the MMM-ISA program was written in the Python 3.8, and the interface of the software was developed using the Tinker library. The image analysis algorithms and analysis tools were implemented using the PyDICOM, OpenCV, and NumPy libraries. This program is included as a part of version 2 of Deep Image Translator software, which is available on SourceForge. Now, for our test of the MMM-ISA, we selected whole body CT scans and FDG-PT PET scans from 10 patients. They were downloaded from the ACR-IN via the Cancer Institute archive. And we specifically chose this database since it contained co-registered whole body PET and CT scans. And so CT and FDG PET images were loaded into the AMIDE software. For each patient, 11 spherical ROIs in the subcutaneous adipose tissue and 3 spherical ROIs in the lungs were drawn in different axial positions based on the whole body CT image. ROI statistics were subsequently generated for the co-registered PET images. And now we use 36 axial slices from the 4,188 axial CT images from the 10 patients for manual semantic segmentation using with the GIMP, the GNU Image Manipulation Program. For the background, the lungs, bones, brain, subcutaneous and visceral adipose tissues, and other soft tissues by labeling these regions by color coding these regions. And the 36 training samples, they were considered more than sufficient since we have previously shown that the models, the deep learning models, can be trained to achieve a high accuracy with as little as 17 images. And so CT image segmentation map pairs were then loaded into the deep image translator, which is the deep learning software that I've discussed earlier, to train a deep convolutional neural network with 1,000 training epochs. The final model was used to to perform automatic semantic segmentation of the total 4,188 axial CT images from the 10 patients, in less than 10 minutes. And we have also shown that the generalizability of such an approach for automated segmentation to be excellent. Now, for each patient, the original PET and CT scans were loaded into the MMM-ISA program, along with the semantic segmentation maps that were produced by the training model, the convolutional neural network model. In this study, we chose to extract FDG uptake from the lungs and subcutaneous adipose tissue by extracting the regions of the model generated segmentation maps containing yellow and red pixels, respectively. So the yellow represented the lungs and the red, the added subcutaneous adipose tissues. And so statistical analysis were carried out using the GraphPad Prism version 9. Pearson's R values were computed using for the correlation between organ-specific FDG uptake measured using multiple manually selected ROIs and FDG uptake determined using the deep learning generated segmentation maps. And so our results. In general, regardless of the number of ROIs used, manually measured FDG uptake in the lungs and subcutaneous tissues, adipose tissues, was well correlated with that calculated with the segmentation maps using the MMM-ISA program. For subcutaneous adipose tissue FDG uptake, the correlation coefficient and the negative log of the p-value increased sharply once values from more than four ROIs were combined. Increase in measurement accuracy determined by the correlation coefficient through increasing numbers of manually selected ROIs plateaued after more than 8 ROIs. Nevertheless, the p-value of the correlation between manual measurement and that using segmentation maps continued to decrease when more ROIs were being used. Similar results were obtained for the measurement of FDG uptake in the lungs. And so in the recent years, numerous open source software tools have been reported in the field of medical imaging processing. One growing area of development is the popularization of deep learning methods through the creation of user-friendly tools with a graphical interface. Nevertheless, most deep learning pipelines for semantic image segmentation generate color-coded segmentation maps stored as image files, while most free software programs for image analysis cannot use these files to generate ROIs statistics for multimodal images stored as DICOM files. So nonetheless, selection of ROIs is an important aspect of in vivo metabolic studies involving PET and CT imaging. In particular, measurements of volume and radio tracer uptake of adipose tissues of many regions, different regions may prove to be important for future studies on the metabolic syndrome, as hypertrophic obesity is related to changes in adipose tissue distribution and alteration in the metabolic endpoints. And so, therefore, we have presented here an update to the Deep Image Translator software by including a tool for multimodal medical image segmentation analysis based on semantic segmentation maps generated using the deep convolutional neural network. Our program can be accessed through the graphical interface, and it allows users to extract ROI's statistics of multimodal images. So, for example, PET and CT scans or PET and MRI, based on color-coded semantic segmentation maps. We showed that organ-specific FDG uptake measured using multiple manually selected small spherical ROIs is concordant with the whole tissue measurements made with the segmentation maps using the MMM-ISA program. Furthermore, we also found that that increase in the number of manually selected ROIs increases the accuracy of organ-specific FDG uptake approximations. And therefore, our pipeline constitutes a simple, automated, and scalable approach to obtain ROI statistics using multimodal scans. Although the accuracy of the neural network will never surpass the accuracy of manually labeled segmentation maps used for model training, our approach would eventually greatly simplify the task of radiologists and researchers who are performing whole body semantic segmentations of multimodal tomography data. And so, yeah, thank you very much for listening.
Thank you for your talk. We have time for any questions. Anybody from the audience? Any question? So I have a question. So you continue to develop the software. What's the direction, further direction?
The direction of this research?
Yeah.
Yeah, that's a really good question. We have developed this part of the research was based on, well, we have previously developed a deep image translator. That's the name, and it's a deep learning software that can segmentate images using a trained model that can be trained using approximately 17 images. So we can use a lot less images to train a highly accurate model for image segmentation. And so this is basically just an update, an added function to our previous program. We found out that most free softwares cannot use DICOM files to extract meaningful medical data from images. So we are using this MMM-ISA that has the ability to accept the DICOM files, and we're using and so we're able to generate statistics using previously generated semantic segmentation maps.
Thank you very much.
Yeah.
Thank you.
Accurate data.
Any other questions? Not, we'll proceed to the last talk of the session.